In chapter 6 we learn how to analyze motion in a plane, a two-dimensional motion. Uh, we represent motion of an object in two dimensions by its trajectory plot on let's say a Cartesian coordinate system, the XY Cartesian coordinate system. Here in the XY coordinate system that I've shown, let's say our object starts at the initial position I and ends up at the final position F. Initial position vector Ri we can write in using the ij unit vector notation by Rix I and plus Riyj. Similarly, we can write the final position vector Rf, and as you can see, the displacement vector delta R then becomes Rfx minus Rix in the x direction, and Rfy minus Riy in the y direction. So the displacement vector delta R takes this form down here, and as you can see in the diagram, Rfx minus Rix is simply the displacement along the x direction, and Rfy minus Riy is simply the displacement along the y direction. Now, taking a derivative with respect to time of the displacement vector, of course, gives us the velocity vector. So velocity vector v then takes the form dRx dt plus dRy dt, or in other words, the Rx dt is simply our velocity along the x direction, and the Ry dt is the velocity of the object along the y direction. So the velocity vector for an object moving in on a plane is simply given by its x and y components. And as you saw above, the position vector for an object that is moving along, moving on a plane is can be given by its x and y positions respectively. Now, if we take a look at the velocity vector and taking yet another derivative with respect to time of the velocity, of course, gives us the acceleration vector. Acceleration, as you know, is dv dt, and which, if we differentiate this equation with respect to time, we end up with dvx dti plus dvy dtj. Well, dvx dt is nothing more than the acceleration along the x-axis, and dvi dt is nothing more than the acceleration of the object along the y-axis. So this is the third equation that defines the motion of the object on a plane, namely the acceleration vector for the object. So as you can see, we have a vector equation for the position of the object, a vector equation for the velocity of the object, and one for the acceleration of the object. In all three cases, the position, velocity, and acceleration in two dimensions is given by they're given by their x and y components respectively. So we need to define the x and the y components of each parameter, each value, to get the vector that we are after. Now, the trajectory plot here, the blue line, is the trajectory plot of an object moving on the xy plane. Now the instantaneous velocity vector, this green vector here, is the instantaneous velocity vector is always tangent to the trajectory plot. So that's a useful piece of information to bear in mind. So the velocity vector for the object at any point is the tangent to the trajectory plot of the object, Now, when there's an acceleration acting, when the object is experiencing an acceleration, A, of course, that acceleration, as we saw up above, has two components, one along the x-axis and one along the y-axis. So our job is to find each component and then use the appropriate kinematic equations to solve for whatever it is the problem is after. Now it's important to differentiate between a position versus time and trajectory plots. And position versus time is either your x or y plot versus t, time, and trajectory plot is position y versus this is a trajectory plot shows the trajectory of the object on a plane, the xy plane in this case. Now, as we had discussed in previous chapters, the slope of the tangent of a position versus time plot gives us the value of the velocity or the speed of the object, whereas the slope of the trajectory plot gives us the direction of the velocity of the object. So the slope of the position versus time, or ds dt, gives us the magnitude of the value of the velocity, and dy dx, the slope of the trajectory plot, gives us the direction of the velocity, or which in this case is tan theta, gives us the angle theta. Now this velocity vector that we have shown here can be decomposed into Vx and Vy components, of course, and the direction of the velocity vector v with respect to the x-axis is this angle theta. As you can see, tangent tan theta is Vy over Vx, or tan theta is inverse tan of Vy over Vx. So once again, as I said, it's a useful piece of information to bear in mind, that you can determine the direction of the velocity of the object moving along a plane by simply looking at the slope of the trajectory at any point. Now the problems in this section, majority of them will be of this form, where let's say the original position of the object at t equals naught is given. Let's say the object has some initial velocity along the x-axis and has zero velocity along the y-axis. Then perhaps the net force acting along the x and the y directions are given, and if the mass of the object is given, then we determine from the net force. So net force along the y divided by m gives us the acceleration acting on the object along the y-axis, and net force in the x-axis divided by mass gives us the acceleration along the x-axis. So we determine the x and y components of the acceleration, And in this situation, in this case, fx net is 0 as is shown here, which means that ax is 0. So our object has 0 acceleration along the x-axis. So if we were to draw a motion diagram, the motion diagram is shown down here. As you can see, the x component of the velocity remains constant because of 0 acceleration along the x direction, whereas the y component of the velocity, oops, I made a mistake in my drawing, let me try it again. The y component of the velocity of course increases as time passes. The red arrows get larger and larger. That's because ay is greater than 0. It's just a positive number. Now here the problem spelled out f net in the y direction is equal to, let's say, 8 newtons. So y is 8 newtons divided by our mass, which is 0.6 kilograms. But had the problem said that f thrust, this we're talking about a rocket in this case, so if f thrust were 8 newtons, then of course ay would have been 8 newtons divided by mass minus g. You need to remember that there's always acceleration due to gravity acting on the object. So that's one thing to remember. Or what I recommend is you always do a free body diagram, and in this case our free body diagram would have F thrust and of course W acting down. So then one would write that sum of the forces in the y direction is F thrust minus W, and that must equal mass of the object times AY, or F thrust minus W divided by M is equal to AY, which is equal to, of course, F thrust divided by M minus a G, which is what we have up here. So you can, if the problem gives you the net force, then of course you don't need to worry about summing up all the forces, because you're already given net force. But if individual forces are given, then I highly recommend that you do a free body diagram so nothing falls through the cracks. Now in this example, this is not a simple example. I'm gonna give it anyways for you to think about a little bit, because this is a good example that highlights the fact that dy dx is gives us the direction of the velocity, or dy dx is equal to tan theta, as we saw up above. Now the physical situation that we have here is that we have a ball bearing which is free to move, very negligible friction surface. The surface is shape of a cup, and as this whole cup is accelerated, let's say to the right, then of course the ball bearing here moves up along the side of the cup to a position that is shown right there. And our task is to find a relationship between the acceleration that the object experiences and this displacement here, which I'm gonna call, what shall we call it, delta x. Let me see, actually let's just call it x, position x. Okay, so this is position x. So if we move from 0 to this is position x, what is the relationship between ax, this acceleration here, and how far to the left the object moves as a result of the applied acceleration? Well, if we draw the forces acting on the object, we have the only two forces, of course, are the weight due to gravity and the normal force. I said that friction forces are negligible. These forces are shown in red in the drawing. Now if we analyze the forces, let me actually clean this up a little bit so I can get rid of this part too. Now if we analyze this a little bit, what we end up with in the sum of the forces along the x direction, we have n sine theta. Now where is theta? Theta is actually the slope of this line here. So if you analyze this, you'll see that n sine theta is equal to max. Now my x direction is parallel like that, and in the y direction I have n cos theta minus w is equal to 0, because the object, the only acceleration that the object is experiencing is along the x direction. And from these two equations up here, we can show that the normal force N is equal to W divided by cos theta, and doing a simple substitution, we end up with this relationship here, where AX is equal to G tan theta. Once again, theta is the angle that the tangent to the trajectory plot makes with respect to the x-axis. So we have AX is equal to G tan theta, but we learned that the tangent of the trajectory of the tangent to the trajectory plot is the direction in which the object is moving, or dy dx. Now we are told that the trajectory is given by this relationship where y is equal to x squared. That's how the cup was manufactured. This is actually the design of an accelerometer, which is used in for navigational purposes. So we have y is equal to x squared. So dy dx, if y is equal to x squared, then dy dx is simply 2x. So now we have, substituting this into this equation up here, we end up with ax is equal to 2gx. Now this is a relationship that equation that relates AX to position X. So how this accelerometer works is by reading off where the position of the ball is along the x-axis, we can figure out what the acceleration that our object is undergoing is at any time. Excuse me. Now, in attacking the problems of motion in 2 dimensions in your drawing, so what you do is you draw your trajectory plot. So here we have our Cartesian XY coordinate system. Our object, let's say, has a launch velocity vi. So the magnitude of vi is either given or we need to figure it out. But there's an associated magnitude of launch velocity, as well as an angle, a launch angle with respect to the x-axis typically. So this launch velocity vi, or v initial, has two components. The components are of course the component along the x-axis and component along the y-axis. So and for each axis we need to know what the acceleration of the object is. Now for a projectile motion is motion of an object moving under the acceleration due to gravity along the y-axis and zero acceleration along the x-axis. That's the definition of a projectile motion. So ax is always 0 in a projectile motion, and ay is equal to minus g, and the shape of the trajectory for a projectile motion is a parabola. So here we have an object which is launched with velocity vi at an angle theta with respect to the horizontal axis. It follows a parabolic trajectory where the acceleration along the x-axis is 0 and along the y-axis is minus g. Now the fact that the acceleration along the x-axis is 0 means that at any time the velocity along the x-axis remains constant. So the velocity at this point along the x-axis of course is equal to vix, whereas the velocity along the y-axis starts at 0. I'm sorry, it doesn't start at 0, it starts at vi y and then gets smaller and smaller in magnitude till it is 0 at the top, at the peak of the trajectory, and then of course switches sign and gets larger and larger in magnitude, but in the reverse direction towards ground this time, till it hits, we have impact with the ground. And the kinematic equations are of course valid. The kinematic equation along the x-axis gives us the displacement along the x-axis is equal to initial velocity along the x-axis times delta t plus 1/2 of ax delta t squared. This term is 0, so we end up with a simple, actually xi is also 0, so we end up with a simple relationship like that. And along the y-axis similarly, this is 0, we end up with y is equal to vi y delta t plus 1/2 of minus g, that's the acceleration along the y-axis, delta t squared. Now from up here we can rewrite delta t in terms of x and vix, and taking this and substituting it into where we have delta t in this equation, we end up with this form, which is y is proportional to x squared, which is an equation of a parabola, of course. Okay, let us now try and do this example here. We have a projectile motion. We know that because the object follows a parabolic trajectory. So we can what we are after, we are given the velocity of the object at t equals 1 second. This is this position right there, and the velocity vector is given as 2i plus 2j meters per second, and we are asked to find the velocity of the object as 0 seconds and 3 seconds. How do we go about solving problems like this? Well, because the object is following a well, it's a projectile motion, so we know that acceleration along the x-axis must be 0, and acceleration along the y-axis is minus, well, a value minus, in this case, gravitational acceleration in planet Exidor, so I can call it gx, for example, minus gx. So if we also know the velocity at t equals 1 second, so at time equals 1 second, the velocity vector is given by 2I plus 2j. That's what's given up here. Now let us go ahead and try and write the velocity vector at t equals 2 seconds. That's this point up there at the turning point. At turning point, turning point, we know that the velocity along the y direction is 0. That's the definition of a turning point. So the y component of the velocity is 0, therefore we have 0j. And since acceleration along the x-axis is 0, that means that at t equals 2 seconds, the velocity component of the along the x-axis must equal that of t equals 1 second, or 2 meters per second. So we just wrote the velocity vector for t equals 2 seconds, but we are interested in finding the velocity vector at 3 seconds. At 3 seconds, the x component is still 2I. So what I'm doing here is writing the vx and vy. I decompose my velocity vector into its x and the y components. So at t equals 3 seconds, the x component is still 2I, but now what about the y component? Well, the y component in 1 second went from 2 to 0. That means that the acceleration vector, if I write the acceleration vector, is, well, as axi plus ayj. Well, my ax is 0, therefore it's 0I, and my ay is a negative number, I know that, but negative what? That's negative 2, because that's obvious by looking at this transition right there, going from 2 meters per second to 0 meters per second. That means the change in the y component of the velocity is negative 2. Well, that change is the same going from 2 seconds to 3 seconds. Therefore, the y component of the velocity here becomes minus 2j. So that's my velocity vector at 3 seconds, then, is 2I minus 2j. Now how about at t equals 0 seconds? At t equals 0 second, well, my x velocity component is still the same, 2I, but how about my y component? Well, y component must have undergone this negative 2 change going from 0 seconds to 1 second, which means that I must have started at 4j to start with. Therefore, velocity at 0 seconds is 2I plus 4j, which is the answer that the question was after. The ball's velocity at 0 seconds and 3 seconds. A good example to show how we make use of the unit vector notation to solve such problems. Okay, let's take a look at another example here. We have an object which is launched at theta degrees with respect to the x-axis, and there is a force F acting on the object, and let's say the object has a mass m, and the initial velocity, the object is at the origin, is at t equals 0 seconds, and the initial velocity of the object is 0, so the object starts at rest at the origin of the coordinate system at t equals 0 seconds. So if we do a free body diagram for our object which has mass m, we have force F acting at theta degrees to the x-axis. We can decompose our force into Fx and Fy. It's x and y components respectively, and of course our W weight vector. So now our next task is to find acceleration along the x-axis and the y-axis acting on the object. X-axis is simple, the only force along the x-axis is Fx divided by m gives us our Ax, and looking at our free body diagram, Fx is nothing more than F cosine of 45 degrees. Similarly, Ay is the sum of the forces along the y-axis, which is Fy minus W, and Fy is F sine 45 degrees, W is mg, so Ay then takes this form. So that's our acceleration along the y-axis, and this expression here is the acceleration along the x-axis. Now we can go ahead and use our kinematic equations. This is for position or displacement along the x-axis, and this is for position along the y-axis. Now the motion of an object on a plane or in two dimensions, the motions along the x and the y axes are independent of each other, so you can go about analyzing them independently. The only common factor between the two is the delta t. So delta t is the only thing that links these two equations to each other. Now by looking at the expression for displacement or position along the x-axis, we can come up with an expression for delta t in terms of x. Let me clear that and redraw it. So this is our expression for delta t in terms of x, which you can now go ahead and substitute in this equation to end up with an expression for y in terms of x. Okay, simplifying this equation, we end up with y is given by this equation right there. So now if you're interested, for example, in finding the direction of the object at any time, what we can do is take the derivative of this expression dy dx, which is simply 1 minus root 2 mg over f, and what this says is that if in my xy coordinate system the object would move in a straight line. As you can see, this is a straight line because we have an expression which is y is equal to a constant times x. So there is no x squared term. Had there been an x squared term, of course it would have been a parabolic function, but this is a simply equation of a straight line. So we know that the object is going to move in a straight line. It's going to follow a trajectory with slope phi. Notice that the launch angle was 45 degrees as indicated here. It's 45 degrees, but the The slope is given by phi, where phi is where phi is equal to 45 degrees if g is 0. So in this expression, if there is no gravity, if you're out in mid-space, if gravity is 0, then dy dx becomes 1, and if dy dx is 1, remember dy dx is equal to tan of the direction in which the object is moving, and if this whole thing is equal to 1, that means that phi is equal to 45 degrees. However, if gravity is not 0, then phi would be is an angle less than 45 degrees. So in 0 gravity, the object would follow a straight trajectory like this, where this angle here is 45 degrees. But in the presence of g, then the slope would be less by a certain amount. And that certain amount can be figured out easily by analyzing this equation and equating that to tan of phi. So tan of phi would equal 1 minus root 2 mg over f. Okay. And if one were to try and figure out what would be the minimum launch velocity, launch force rather, that the object needs to have, then one way of going about analyzing this is saying that, okay, for the object to take off the ground, then we need a trajectory which is just more than horizontal. So if the slope of the line, if the trajectory is horizontal with the x-axis, that means the object never takes off the ground. And what we mean by a horizontal trajectory is that dy dx is equal to 0. So in the expression that we obtained for the trajectory, that's from up above. So the trajectory was given by this expression here. If we say that, well, at f min, minimum force, dy dx, if we set dy dx to 0, then we end up with, if we analyze this, we end up with force of root 2 mg, which means that if the launch angle is 45 degrees, then we need a minimum force of this amount such that the object takes off the ground, of course. So using these calculus techniques, these are simple calculus techniques, it's rather straightforward to answer these questions. Intuitively, of course, you could have answered this question by saying that, well, for the object to take off, then this is the xy components. We said that the thrust force is at 45 degrees, and we also have W. You could have said that, well, then the y component of thrust force, Fy, must be greater than or equal to W, and if you do the same analysis, you'll end up with the F being equal to or greater than, in this case that would be sine of 45 degrees, and W, which is greater than or equal to square root of 2 mg. So either way you would have gotten the same answer. I'm sorry, what I meant to say here is that sine of 45 is on this side, not this side. So if you bring it, so this is 1 over root 2. So that'll be f over root 2 greater than or equal to mg, which makes it f is greater than or equal to root 2 of mg. If you look at this free body diagram here, fy is equal to f sine of 45 degrees, and sine of 45 degrees is 1 over root 2, so that's f over root 2, and for the object to take off you need fy greater than or equal to w, which gives you this expression here, which is the same result that you end up with if you use the calculus technique by saying that, well, I need the derivative of my trajectory to be greater than or equal to 0 for the object to launch. What I like to do the next lectures is cover relative motion, as well as do a number of examples of motion in 2 dimensions and relative motion, and in particular do a few examples from the end of the chapter problems.